Before we even talk about breadboards, it is important to understand that this isn't the only way to build a circuit. In fact, it is one of the several methods, each with its own advantages and trade offs. Traditionally, circuits are built on a printed circuit board or a PCB or sometimes a prototype wire board. It is designed to connect the circuit components permanently exactly as intended. This is what you would find in almost all finished electronic products or in prototype hardware projects. It is reliable, compact, and optimized for the application. But the is that it is not at all flexible. Once it is made, changing anything means redesigning and manufacturing a new board or resoldering the components onto the wearer board. Another method is point to point soldering, where components are directly soldered to each other or to terminals without a formal board layout. This is also common in prototyping and also older electronic designs, and sometimes in high power or high voltage applications. While it can be very robust if done well, it quickly becomes messy, hard to debug, and difficult to modify because of the mess of the wires which are present. One wrong connection or a change in design can mean a lot of rework. That that's where the breadboard comes in. A breadboard is designed specifically for prototyping. You can build, test, and modify circuits quickly without any soldering. But to use it properly, you have to understand what's happening inside because from the outside, it doesn't show you how things are actually connected. Internally, a breadboard is made up of rows of metal clips, often called spring contacts or sometimes referred to as butterfly contacts. Because of their shape, each of these contacts is designed to grip the leads of the components and wires securely when you insert into the holes. More importantly, these metal clips connect multiple holes together underneath the surface. If we look at the main section of the breadboard, each horizontal row of holes is electrically connected by one of these metal strips. That means if you insert two component leads into the same row, they are effectively connected together. They become the same electrical node. This is one of the most important concepts to understand because a lot of mistakes come from assuming holes are isolated when they are not. The entire point of a breadboard is simply that it allows you to connect different components to each other. On the other side of the breadboard, you will usually find long vertical columns called power rails. These are intended to distribute the power and ground across your circuit. However, something that often surprises beginners is that these rails are always not continuous along their entire length. Many breadboards have a split in the middle, meaning that the top half and the bottom half of the rail are not connected unless you explicitly bridge them. If you don't realize this, you can end up with a circuit that looks correct but simply does not receive power. In the center of the breadboard, there is a gap that separates the two halves. This gap is intentional. It allows you to place integrated circuits so that each pin sits on a different row, preventing accidental shorting between pins. The rows on the left side of the gap are not connected to the rows on the right side, so this is separation that is critical for proper integrated circuit placement. Because everything relies on these internal metal contacts, the quality of the connections matter. If a wire isn't fully inserted or a component lead is significantly bent or loose, the connection may be intermittent. This can make debugging frustrating because the circuit might work sometimes and fail at other times. There are also some fundamental limitations to breadboards. The internal contacts introduce small amounts of resistance and capacitance, which usually don't matter at low frequencies, such as the sub 10,000 kHz range and lower, but can affect performance in high frequency or sensitive analog circuits. We are looking at circuits operating above 1 MHz. Additionally, breadboards are not designed for high current, so they are best used for low power prototyping. So while breadboards are incredibly useful, they are not magic. They are just a structured way of making temporary electrical connections. If you understand how those connections are laid out internally and how the components are compared to more permanent methods like PCBs or point-to-point wiring, you can use them effectively and avoid a lot of common mistakes. So let's start with the breadboard tutorial. So I have taken a simple breadboard. In this case, this breadboard has two power rails. It has one middle section. This breadboard is made up of three sections. So if you want, we can remove a section as per we require. So if you want, we can also have a double breadboard with two middle sections and two power rails. But in this case, we will leave it as is. So as I said in the beginning, the power rails are the ones on the top and on the bottom. So in this case, the power rails on the breadboard are continuous. If you look on the left side and on the right side, the red line and the blue line runs from leftmost side all the way to the rightmost side continuously. This means that the power rail is not split and we do not require a jumper. So as I was showing you in the video previously, there was a jumper present. So this is typically how you would place a jumper. This jumper is used to connect the left side and right side to each other. Internally to the breadboard, the connections are in this manner. So all of these pins are connected together in this orientation. So if you observe, column number 1, A, B, C, D, E are connected to each other. Column number 2, A, B, C, D, E is connected to each other like this. And then column number 3 all the way to the end of the line. The same applies to the bottom half. F, G, H, I, J are connected to each other. One thing to again remember is that E and F are not connected to each other because there is a split in the breadboard. This split does not allow the connection to be present from E to F. You have to make the connection manually. So if you want to make the connection, you have to make it in such a manner. Then A, B, C, D, E, F, G, H, I, J are connected to each other. So we will see that. So then let's look at how to place components into a breadboard. Let's take an example of a simple transistor. So this is a transistor. 3-pin device. It could be either NPN or PNP, BJT. It could be a MOSFET. It could be a JFET. So this transistor is placed in this orientation such that each of the three legs are connected to different columns. So in this case, it is connected to column number 19, column number 20, and column number 21. If you observe closely, the three legs of the component are connected to different columns. Column number 19, column number 20, and then column number 21. This is the correct orientation for the transistor. If we want the top half of the transistor to be connected to the bottom half of the breadboard, we have to run a wire in this manner. Then these three pins on the top A, B, C, D, E, F are connected to G, H, I, J on the bottom. The wrong way of placing the component in the breadboard is such that the component legs are in the same column. This is an extremely common mistake that students will make. They will place the component in this manner such that all of the legs are in the same column. So in this case, let me place it in column number 20. So it is in column number 20B, column number 20C, and then 20D. So each of the legs of the transistor connected to the same column. 20A pin, 20B pin, and 20C pin. Sorry, 20B, 20C, 20D pin. Now these three pins are connected to each other and effectively shorting the transistor to itself. So this will not damage the transistor, but this will not allow the circuit to operate. So again, the correct orientation for the transistor would be in this orientation, or it would be in this orientation where it is, yeah, this orientation. So this is the correct orientation for the transistor. So let's just build a simple circuit with an LED and a resistor to see how the breadboard would work. So let's take a 12-volt power supply. Let's place this 12-volt power supply near the breadboard so we can effectively connect it to the power rails. So I will take this and connect it to the power rails, to the positive and to the negative. Now my power supply is connected to the positive and the negative rail of the breadboard. Next, what I'll do is that I will connect the top half of the power rails to the bottom half of the power rails. I will do this by running a wire. So even though this is plus on the top as well as plus on the bottom, these two are not connected to each other unless we run a jumper wire like this. Then I will run a jumper wire from negative on the top to negative on the bottom. Now the entire breadboard power rails are energized. The top power rails and the bottom power rails are energized. I'll just remove these jumper links because they are redundant. So again, the top half of the breadboard and the bottom half of the breadboard have the two power rails. These two power rails have now been connected to each other. So now the power will flow from the top power rail to the bottom power rail. So effectively giving us option of using both of them. So then let me take a resistor and place it into the breadboard. I will place it on the positive side in this manner. So now the power from the positive power rail reaches pin number 19A. Then I will take an LED and place it in the breadboard as well in this orientation. So now the resistor leg is connected to the power rail on one side, and on the other side it is connected to the leg of the LED through the breadboard. So as both of the legs of the components are in column number 19, they are connected to each other. Then on the other side there is a breadboard split. Other side of the LED is connected to 19, but on the right hand side. Right hand side if you look on this orientation, or the bottom side if you look on this orientation. So now we have to connect this LED down to ground. So for that we will use a jumper wire. So I'll just take a green wire and connect this down to ground. So now we have a complete circuit. The power from the power supply will flow into the positive power rail through the LED, then down to ground. The ground is connected from here through this green jumper wire up to the black wire of the power supply. So if we turn the lights off, we can observe the LED working. So now you can see the LED is working. We can increase the power supply voltage to increase the brightness of the LED, or decrease the power supply voltage to decrease the voltage of the LED. So that is it for the breadboard basics.